I want to finally start to move away from diatomics. Because I want to do something a little more interesting. There's so many diatomic molecules in the universe, and most of the combinations of two atoms don't even really make stable molecules. But that's not really the point of why we spend so much time on diatomics. It's not about the fact that their theory is relevant necessarily directly, but indirectly, it's extremely essential. Right? It's a bootstrapping method where we can understand more complex ideas, more complex systems by using a diatomic as a framework for the system. Right? The idea is that we're going to treat the vibrations of a mini atom molecule as a combination of diatomics. We're going to have to figure out how that math's going to work. Right? How do we take a complicated molecule and kind of decompose it into a bunch of little diatomics that you know how to solve? That'll be a little tricky. But that's kind of where I want to focus. And what we're going to see is that it's going to get a lot of push. Like we're going to have to push through this theory, just try to understand how we can apply diatomics to beta molecules. And then once we have that set up, we're not going to go through like the detailed math of it, but we'll basically set up the problem, and then the math will just simplify, and we'll get to that result that we want, which is that we can treat the vibrations of any molecule of any size as a combination of diatomic looking vibrations. Okay, so this idea that every vibration is a Morse oscillator that has an energy with a frequency, some inharmonicity, it's got a quantum number, it's got some potential like this, a Morse potential. We're going to see that molecules can be represented as a sum of many of these. And so we basically, and what it'll separate out to is a bunch of separate ones that correspond to each of the vibrations of a molecule. Okay, so this theory will come back to haunt us. That's really nice that we have this really complex system that reduces to just a series of these Morse oscillators. We have to figure out how many we need, how many Morse oscillators represent a molecule, and kind of how do we construct them. And that's going to be our goal today. The reason why I like to teach this is because it teaches us this bootstrapping, that we can take a simple problem and understand it completely, and then use that understanding to solve something more complex. Bootstrap our understanding from simplicity to something more complex. We're going to see that when we construct molecules from atoms. We're going to do exactly the same process. We're going to understand an atom completely, and then we're going to add them together to make molecules. We're going to bootstrap molecules from atoms. So we can bootstrap big vibrations from single vibrations, and the same idea. But let's look at that math today. So I've already answered this question for you a while back when we talked about Born-Oppenheimer approximation. But the big question I want to answer today is how many unique vibrations does an N-atom molecule have? All right, and we wrote down, I actually answered this question for you, and we talked about the flies and the elephants. We can use the Born-Oppenheimer approximation to break down all the possible ways molecules can move. And we came up with a nice formula, and we're gonna look at this formula a little more carefully today. But the answer is for a 3D molecule. Right? And I want to put an asterisk next to 3D molecule because there's a little subtlety here. But the number of vibrations is equal to 3n minus 6. Well, I'll have to specify that this number can change depending on the type of molecule we're looking at. It's not a complicated argument. This number isn't always accurate, and we'll understand why. Right, and so what I want to do now is I know what my end result's going to be. Got N atoms connected through bonds, and I know at the end I'm going to be able to write the vibrations of the system down into 3n minus 6 separate vibrations, and so that's my goal. Somehow I can take a molecule that's got all these atoms and simplify it so that I know I have that many. So let's just kind of like make up a schematic molecule and kind of analyze this a little bit. And see if we can identify the problems of identifying these 3n minus 6 vibrations. So I'm just going to make up a generic molecule. And I mean, so generic it doesn't even look like a molecule. But imagine I have some atomic system that looks like a bunch of balls with springs. Right? It doesn't matter what it looks like. Maybe we've got something that looks like this. Okay. And I've color coded them for no particular reason, but other than to identify them in a second. Right. And so let's think again about identifying the vibrations in this system. And of course, what you would initially think is, well, we can identify pairs of atoms diatomic, right? That's the first way we could think about this. I say we know the diatomic problem. We know how to solve for a diatomic vibration. Well, let's just do the simple thing and break this molecule up into pairs of connected atoms. So I could, for instance, identify this pair of atoms. And I'll label them A and B. I could certainly identify a pair of atoms B and C. And we can also, for instance, look at this one here. So I'll write D. A. Right. Then, of course, there's lots of different pairs I can choose. Right? But I've identified 3 different diatomics that can vibrate. Okay, so identified 3 diatomic pairs. AB, BC, and AD. Okay. You can think of these as carbons. It doesn't matter. Okay. They all have, you just think they all have covalent bonds, right? Just a normal molecule, nothing fancy. I don't want anything exotic here. So let's think about now. Let's think about, remember, in order to solve for the wave functions of this system, we need to know something about the potential energy, right? The potential energy of the spring. So the question I need to ask now is, imagine now we excite one of these diatomics. Say, for instance, I stretch A and B. So as I stretch the AB pair, okay, what does that do to the atoms? Think a little bit about, well, here's an interesting idea. Let me give you an idea, right? I want to think about what happens to the other bonds as I move AB. In some sense, are these independent of each other? Is the potential energy of BC stretch independent of the AB stretch? All right, I want to think about the independence of these stretches, because remember what I want is I want 3n minus 6 unique vibrations. You can think of them as independent motions. And so what that would mean is that if I move AB, that potential energy, the change in that potential energy should not affect BC or AD. So if stretches are independent, the BC and AD stretches should be left unchanged. Okay, that's what I mean by independence. And that would mean that I could think about the AB independently of the other ones, because the other atoms are basically held into place. And it's just that single local vibration that's happening. But we're going to find that that does not work. And let me give you an example why this doesn't work. Not true here. And why? Question is why. So we'll call this like a counter example. Right, I'm going to replace, sorry, I got to replace one of these hydrogens with deuterium. Okay, so here's methane with a deuterium. Okay, and let's do the same concept, the same idea as I have up here. I stretch the CD bond. I'm going to start pulling that D away from the carbon. And I want to ask the question, are the other hydrogens, their bonds with the carbon left unchanged? Right, so my question, in some sense, is if I say, I'm going to do a little bit of geometry notation. Imagine these bonds have some length and some ability that I mark with one, right? Well, one dash, like when you show parallel lines or equivalent lines in a triangle in geometry class, you mark them. And I'm going to stretch the CD bond, right? And the question I have now is, are these CH bonds changing or not? Right? I've stretched the CD. And the question is, are all of these equivalent still? Right? Can I just think of that cleavage is just basically the whole molecule itself is just standing still, and I'm pulling that deuterium away from it? The answer is no, because what happens experimentally, right, is that as you start to pull that atom away, right, I'm doing what's called a homolytic cleavage here. I'm taking one electron and taking it away and leaving another one there and just cutting the bond. Now, what happens in this intermediate when it's stretched is that the hydrogens on the carbon change geometry. So here, right, the angle is 109.5 degrees. Right? Remember the tetrahedral. But as you start to pull this system out, it turns into an equilateral triangle, a planar one, where this is 120 degrees. So what you get is a triangular or a trigonal planar methyl radical and a deuterium radical. By definition, these bonds are now different. This is a completely different molecule than this. All right, so what that means is that the vibrations of these have to be different than they were before. Right? It's just a totally different molecule. CH3 just has completely different stabilities than CH4. So what I'm going to say, and there's other consequences that come from this going from tetrahedral to planar. There's other consequences vibrationally from this. We don't have to worry about that. If you take spectroscopy, we will learn. But the idea is that changing one diatomic stretch in my polyatomic molecule affects all the other ones. Right? Now, if the molecule is big enough, it may not affect ones far away. So there's some locality to it. Imagine that I have some, like, instead of methane, I have like octane. And I have a deuterium at one end and I pluck it off. The carbons way on the other end don't really care. They don't even see it. So I should say all other nearby bonds and their structure. Or I say their energetics or structure. So we can't just break the molecule down into diatomics, right? It just, it doesn't leave you, it leaves you with a bunch of dependent vibrations. We stretch one bond and it affects all the other ones, right? So that's not going to work. You can also figure out that if you use this pair-like system, if you pair all the atoms up and count all the possible pairs, it doesn't come to 3 n minus 6 anyway. So it doesn't work mathematically. All right, so we have to figure out how to, I think it seems this is a reasonable approach. We have to figure out some way how to take this approach of stretching diatomics, right, in some way to make it so that they're all independent, right? We have to try to find some way to do that. I know that there's some way to independently to do it, because I know when I go into experiment, I see there are 3 n minus 6 independent vibrations. Experimentally, I know that. So I know there must be some way to represent this molecule and its vibrations in a way that where the vibrations are all independent of each other. One doesn't affect the other. Okay. So what we're going to do is find a different set of coordinates for our molecule. Right, what we're going to define now so instead of pairs of atoms defining our vibrations, we will use full combinations of all atoms vibrating. And they have a special name called normal modes. Right? I want to talk a little bit about normal modes today. Okay. What we're going to find, a little bit of math, is that the independent vibrations of the molecule aren't just vibrations of a given bond, but they're entire collective vibrations of the molecule that satisfy certain properties. And the properties actually, the only property that it has, there's 2 properties it has to solve. The first one's quite simple. They all vibrate such that the center of mass of the molecule is left unchanged. Okay. We're going to look for special motions where all the atoms are displacing. They're all moving, but they're all moving in such a way that the moment of the center of mass doesn't move. So if you have some hydrogens displacing in this direction, there has to be something moving in the opposite direction to cancel it out. Okay. So the way we're going to construct this the first thing we're going to do is we're going to take our molecule. I'm just going to copy it over. You guys can draw whatever you want on your page. It doesn't matter. Whatever molecule you want. I'm just going to use what I have. Right. Oh, yeah, there we go. I'm gonna highlight each atom. So this is, we'll call it atom I. Okay. Here's atom I. And atom I has 3 coordinates. Right? It's got some coordinates x sub I, y sub I, and z sub I, and they're defined relative to the center of mass. We'll put the center of mass in this big red spot here. Okay, so I have this vector pointing at this atom, R. Sorry, I had to write over this. And you have some displacement vector, R, for the atom. That just tells you where in around relative to the center of mass that atom is. Okay, so there are, if they're in atoms, then there are 3 n coordinates. Okay. So that means that there are total 3 n displacement coordinates. And what I'm going to do is I'm going to displace each of the atoms individually. Displace each one of them individually along each of the coordinates. And I'm going to ask the question, how does the potential energy of the system change as I displace one of the coordinates? Remember, all I care about is the potential energy. That's what determines my system, my wave functions, my energies, is the potential energy. Right, so I want to define the potential energy as a function of 3n displacements. Okay. I want to think about how the energy of the system moves as I move each atom along each coordinate. That's a really nasty thing to write down when you have this many atoms. Why I want to find some simplification. So imagine if I have benzene that's got 12 atoms, that's 36 different coordinates you have to consider. Kind of a pain in the butt. And so what I can define is the potential energy. And the potential energy is a function of the displacement of each coordinate. Right, so what I can write for the first coordinate of the first atom, I could write x1 minus the coordinate at equilibrium. All right, remember these are springs, so if I don't touch it, the system is at some equilibrium geometry. The atoms are just sitting in space where where everything likes to be at minimum energy, everything's relaxing. So this is the equilibrium coordinate, and so I'm stretching it relative to that. And of course, there's a y1 minus y1e and a z1 minus z1e. And it goes all the way to zn, sorry, 3n, excuse me. Oh, no, there's n atoms, sorry, minus zn sub e. Right, so it's this big, long function that measures how the potential changes as we move away from equilibrium. Right? How do we calculate that? Well, what we're going to do is just assume that the system moves away, increases or decreases its energy as we move away from the equilibrium point as a polynomial. Okay, there's going to be a linear part, a quadratic part, could be a cubic part, I don't know, right? There's going to be some polynomial, looks like a well, as we know, the harmonic oscillator, right? It looks like a quadratic function near the bottom of the potential. So we know that the potential energy is going to have some quadratic behavior. At the very least, it's going to look quadratic. So what that's going to look like is first the potential evaluated at equilibrium. Right, that's just a number, right? So this is the potential energy at equilibrium. Okay, so that's our constant part of the function. Now we have a linear part of the function. Right, I'm going to write this out a little wider, so we've got to fill it in. So that's going to look like x sub I minus x sub I e, right? You're going to have this linear part of that equation. Right? And we have to add a slope to it, right? It needs to have a slope for it to be aligned. So the slope is the derivative of the potential at that point. So I could write next to it the slope, which is the derivative of the potential with respect to the coordinate evaluated at equilibrium. And there are n of these. There's 3 n, right? Because there are 3 coordinates per atom. They're in atoms. So there's 3 n of these slopes. All right. So I'm going to have a sum of I from I equals 1 to 3n. So this is my displacement, my linear displacement and energy as I move, as I stretch. Right? And now we know we need to have a quadratic part. Okay. But remember, a quadratic is a coordinate squared, and we have lots of different coordinates. So I could move the same coordinate twice. Imagine thinking of the second derivatives as 2 coordinates stretching simultaneously. So I could have a square, I could have the same coordinate and be square in that coordinate, or I could have 2 different coordinates stretching linear. So I actually have 2 sums here. I equals 1 to 3n. Oh, sorry. I equals 1 to 3n. J equals 1 to 3n, right? I have to move 1 coordinate and then multiply that coordinate by another coordinate displacing. So I'm going to have x sub I minus x sub IE times x sub j minus x sub j e. And then I have the slope of this. I got to add a 1/2 to it. Half. And then I have to have the coefficient on the quadratic, which is the second derivative function. So that's the second derivative with respect to the 2 coordinates, where x sub evaluated at the minimum where both of them are evaluated at the equilibrium point. Okay, remember this is a slope of the curve at the minimum point, at the equilibrium point, and this is the curvature of the function, how sharp the quadratic function. So kind of complicated, but all I'm doing is I'm just saying that my energy, when the energy is changing in my system, it's at some initial value, and then the energy changes as a sum of a linear combination, a linear change in coordinates, something proportional to the linear function coordinates, plus a quadratic, right? It's just a simple Taylor series approximation, polynomial. This looks like mx and this looks like bx squared. We can simplify this. So I'm gonna copy this over to the next page so we have it. I know it's ugly, but we can make some simplifications to this. First of all, I can say that the potential energy at equilibrium is just 0. Right? That's the ground state. It's the lowest possible energy for the molecule. Remember what I said to you guys, for you to get one of me, molecules like to be lazy. They like to be at the lowest possible energy. So what we can just do is say that potential energy is minimal, can't be any lower than that. And so we can just set it to 0. Just by definition. Right, this is at the bottom of the potential. It's the minimum energy. The minimum V possible. Okay. This second term, this linear term, also goes to 0. Why does it go to 0? Remember, we're at the bottom of the potential, the equilibrium point, which is where we evaluate these slopes. This is the slope of the potential at the minimum, at equilibrium. Well, that's 0 because you're at the bottom of a parabola. So this is 0 because we're at a minimum at equilibrium. This is 0 because the way that this looks like at equilibrium, this is V and this is X sub I, you have some potential that looks like this, and X sub IE is this point right here. It's at the tangent of that curve, of course, is 0. It's at a minimum. Okay, so that goes away. So all we're left with is the second derivative, which tells you something about the curvature of the function. But remember, we're at the minimum. This is going to be, because we're at a minimum, the second derivative has to be positive. It's convex up at a minimum. Right? It just looks like this at the bottom of that potential. So it's positive. This number is always positive. I should say it's greater than or equal to 0. It could be 0. It's always positive. And we know, we have an idea of what this second derivative is from our diatomic potential. If I write, so what I can do now, let me just simplify this so that we can say that the potential now, do a different color. I don't use this symbol very much, but these 3 dots means therefore, just a small. Sorry, 3n is equal to the sum of 1/2. Oh, sorry, I missed a sign. Uh, 3n, I equals 1, j equals 1 of the second derivative with respect to those coordinates. I'm just going to write it more simply as xi xj. What does this look like? Well, it looks like a parabola. Let me write, there's a 1/2 that needs to come in here. I keep forgetting to write the 1/2. Right, remember for a diatomic, this potential, V of x for the diatomic, looks like 1/2 x squared times k. So what I have here is a multidimensional harmonic oscillator potential. I've got the x squared. I and j might be the same coordinate. Might be some 2 different coordinates. I don't know. But the second derivative is just the force constant. It's the stiffness of the potential, the stiffness of this motion as a function of these 2 coordinates. As I stretch these 2 atoms in 2 directions, this second derivative tells me how stiff the connection is as they move. So these second derivatives are force constants, or Hooke's law constants, spring constants, or whatever term you like to use. Right? But I have lots of them. Right? Every pair of atoms, every pair of coordinates gets assigned a force constant. Right? So I can write this instead, even more simple. As the sum over 2 sets of 3n constants of 1/2 a force constant that's labeled by the 2 coordinates times xi xj. Right, I've used f here just because you could use big K if you want, but we typically use f. So my potential, it looks like the harmonic oscillator potential. It's just over multiple dimensions now. Right, all the different coordinates of the system. Diatomic, right? I get the diatomic system out of here. get the diatomic potential out of here, if I set n to 1, that means I have a sum over I equals 1 to 1, j equals 1 to 1. So this is f(1,1) times x1, x1, and that's just k x squared. Right? There's only one coordinate in the diatomic, just one displacement. So I've got this formula here, right? And so what this says is that at minimum, or say at worst, a molecule is has 3n by 3n force constants or vibrations. All right, well, that really sucks, right? That's really scary. Right? It's even worse than we originally imagined. I said that maybe we could represent molecules as diatomics. And so you only have to count the pairs of atoms, and that's less than 3n minus 6. In reality, in order to fully specify the system, I need 3n times 3n numbers. It's 9n squared. That's a big number. We have to find, again, some way to simplify this. Right? We have some construction that allows us to think about how the force of the energy changes as I move each atom in certain directions. But I've got 3n times 3n. It's fun. We can make some simplifications to this. Once again, continuing to make simplifications. I want to think about the structure of these force constants as a collection, not individually, but do they have any special symmetries? If there's anything that we can simplify in those. All right, so what I'm going to do is I'm going to make a table of them. All right, so we're going to make a table of the Fij entries, where we're going to put rows and columns. Okay. So I've got this F, we'll call it F. Right. And we're going to put it in a big spreadsheet. All right. It's got columns. And it's got rows. In this direction, I can label each of the columns and rows of each of the coordinates. 1, 2, 3, 4 to 3n. 1, 2, 3 to 3n. Okay, and I can just start filling in. Right? I can just start moving, displacing all of my atoms and seeing how my potential energy changes, and calculating the force constant from that displacement. So I've got one F11, F12, F13, F13n. I'm not going to fill all this in, obviously. You guys get the idea. I've got these diagonal ones where the coordinate, we're looking at the square of the coordinate. They're kind of like the diatomic displacements. We've got all of these up. And I can go on the other, I can go down the rows too, right? I can have F12, F13, and so on and so forth. Right? Of course, you guys should, if you're clever enough, you should know that this is not a table, but a matrix. What are some simplifications that we can make to this table? What are some symmetries we can look at? Well, here's the trick. If we go back to the potential, right, the force constants are proportional to displacements of two coordinates. Well, it doesn't matter if I switch I and j here. It's the same thing because everything's commutative. So every ij has the same displacement as every ji. Okay, there's a symmetry between these two labels. Okay, so what that means is that everything in the top triangle is mirrored to everything in the bottom half of the triangle. So around this diagonal, the elements on this side are the same as this. Right? They're mirror images of each other. right? Note due to commutativity, commutive, let me spell that right. Commutivity, Fij, which is proportional to Xij, is equal to Fji. Okay. So in fact, I don't actually have 3n by 3n elements that are unique. I only have the diagonals and then everything up here, because everything out down here is copied. All right, so you can kind of identify that these two are the same. I'm sorry, this is I screwed this up. This is 2-1. And this is 3-1. Apologize. And these are connected, right? You can see that they're just mirrored to each other because of algebra. Right? It turns out that there's a really, and here's another thing, right? The other thing is that for all, let me not use that label. Sorry, I'm having my math minor come out. For all I, all j, Fij is greater than 0, right? Because remember, we're at the force constants are measured at the bottom of the potential, which is always convex up. So it's at a minimum, therefore the second derivative is always positive. So what we have here is so F here is a positive, what's called a positive definite, which means that everything is positive, symmetric, square matrix. Right? Same number of rows with columns. It's symmetric about the diagonal, and it's positive definite. And all the values are positive. There's a theorem in linear algebra of matrices, that if you have a matrix that looks like this, you're guaranteed to be able to do something to it simple. For any matrix of this kind, there exists an equivalent matrix in a different coordinate system. All right, not X, Y, Z, but some other coordinate system that we can select such that F only has diagonal elements. All right. So what I can do is I can take my little coordinates, my X's and my Y's and my Z's, and I can add them and subtract them together in special ways. I can create collective coordinates. And if I instead think about the force constants of the system along those special collective coordinates that are sums of different motions, I can always choose the set that gives me only values along the diagonal. What does that mean for them to be along the diagonal? Well, remember what I said about motions that are correlated. If, let's say, for instance, F21 is non-zero, that means when I move coordinate 2, it affects the force along coordinate 1. Right? So think about the second coordinate being some atom, and the first coordinate being another atom. And if F21 is non-zero, that means if I move atom 2, it affects the force constant for atom 1. Right? They're correlated to each other. So off-diagonal elements correspond to dependencies between the vibrations, between the displacements. If the whole thing is diagonal, then they're all independent of each other. We have 3 independent coordinates. They don't interact with any of the other ones. So I'll write that here just to kind of clarify. This means displacement along coordinate 3 affects coordinate 1. right? So these are coupled motions, coupled displacements, right? But think about that same interpretation for the ones in the middle. This is saying if I move along 3, this element tells me how it affects coordinate 3. Okay, great. This is just something that tells you something about that specific coordinate. So if I could choose a set of coordinates where they're all diagonal, then they're all independent. So what I have to do now is figure out how to combine these 3 n coordinates together in some collective way to get rid of all the off diagonals. That's a tough problem, but thankfully computers do it for us. Actually, Mother Nature does it for us as well. Okay. So what I can say now is that I can define a new f, an f prime, which is still 3n by 3n, right? But it only has force constants along the diagonal. And you got big zeros here, right? So this is equal to 3n distinct, independent displacements. Okay, so that means then that my potential is are these special coordinates. We have to figure out what they are, right? Because the coordinates along the columns aren't x1, x2, x3, x4 anymore. There's some new coordinates, right? I'm going to call them q1, q2, q3 to q3n, q1, q2 to q3n, right? So we have new coordinates, right, which are called q sub I, and they're proportional to, but not exactly equal to, the sum over I equals 1 to 3n of some number c sub I times x sub I, right? Where c sub I is just a number between 0 and 1 that determines how the coordinates mix. Right? There's a whole process of determining how we take these coordinates and put it into these. Okay, I actually have a whole book in my office that tells me how to do it. It's fairly complex. It was a big push in the 1930s. In the 1940s, it's developed this theory of what we call polyatomic vibrations. And these QIs are called the normal modes. And correspond to all independent motions that leave center of mass unchanged. I don't know why I wrote this in all caps. Just seemed like it was worth emphasizing there. Normal modes. These normal modes are what we call vibrations. Okay? And each of the vibrations, right, are dependent only on this one force constant. So each of these complex motions have a potential energy that just looks like a diatomic. It's just 1/2 times a force constant times the coordinate squared, just like diatomics. Okay, so what we've done now is we've constructed a independent, like collective set of motions that all combine that lead to a potential energy that just looks like a independent sum of diatomic molecules of different strengths. This just says that the potential as a function of this is just 1/2 Ki Q sub I squared, right? It looks, I wrote F, sorry. Sorry, I keep changing that up. Right? Diatomic-like. All right, so everything other than the way that we construct the vibrations and the coordinates, everything looks exactly the same as a diatom. Equally spaced levels, they're slightly anharmonic. You can represent them as a Morse potential, potentially. Everything is exactly the way you would expect. I have a couple more subtleties that I want to talk about here. Remember that I said at the beginning of the lecture that there are 3n-6 displacements or vibrations, but I've just counted 3n. Okay, so 6 of them are irrelevant. Let's figure out why that is. So there are 3n force constants, but I'm going to claim that at most 6 are irrelevant. Right? Let's think about those. We've already talked about this a little bit. Right? Imagine I have this molecule, right? Like this. Here's a molecule. And I displace all of the atoms collectively by the same amount. Right? What if I just kind of move everything in the same direction? Okay, so I have these collective displacements. Where all atoms move with same displacement vector. Well, all I'm doing is I'm just taking the molecule up and I'm moving. Right? That's all I'm doing. I'm not moving anything relative to each other. Everything's moving together. So I'm just taking the molecule and putting it somewhere else. These are translations. And XYZ, right? And so by definition, there's no force for this. You can just move the molecule freely. There's no force on it. So for the first 3, I'm sorry, I counted from 1, not 0. Apologize. Are all 0 because translation displaces no bonds. Okay, so 3 of the 3n constants are 0. We don't have to worry about them. They just go away. Now, what about the other ones? Well, again, take the same molecule. Right, but instead what I'm going to do is rotate them all around the center of mass about the same amount. Right, so I do some angular displacement. Right. So these are collective displacements where atoms rotate about center of mass. Right, and of course, this is just rotations. in XYZ. All right, and depending on the molecule, there's either one, two, or three. There's either two or three of them. Let me show you what I mean by that. Hopefully I have an example. We'll talk a little bit more about this in class next week. Well, let's think I have two different objects here that are rotating. Is this a good object for this? Yes, yes. Here I've got a molecule that's a pen. This is a diatomic molecule. How many unique ways is there to rotate a diatomic molecule? Well, there's this one. There's also this one. Right? So I've rotated it. Okay, let me be specific. So there's this one. There's this one. And see, then there's this one. It's not too hard to convince yourself that this one and this one are exactly the same. Right? All I've done is I've taken the whole system and rotated like this. It's not really a new rotation. So linear molecules only have 2 degrees of rotational freedom. Now look at my book. The book has this rotation, it has this rotation, and it has this rotation. This one, this one. This is the other one, sorry. It's got this one, it's got this one, and it's got this one. It's got 3 unique ones. All right, so a 3-dimensional molecule, a generic molecule has 3 degrees of rotational freedom, but simple molecules like linear molecules only have 2. So 3 force constants are 0 for 3D molecules and 2 for linear molecules. So the total number of vibrations is either 3 n minus 6 or 3 n minus 5. Linear molecules have 3 n minus 5 vibrations, and 3D molecules have 3 n minus 6. There's 3 translation, 3 rotation, 6 total. So 6 of the force constants are 0 for a 3D molecule. All right, so I'll just write that here. Well, I got a little table here. I'm just going to copy from some old notes of mine just to show you the results. Whoopsies. Oh. I want to make this smaller. There we go. So here's a selection of molecules where I've counted the total degrees of freedom. That's 3n. Every single molecule has 3 translational degrees of freedom because there's 3 different directions. And you can see here the difference between each one, right? As you go into larger and larger systems, you have more and more vibrations. But as you can see, the number of vibrations that CO2 and H2O have the same amount of atoms, the same amount of translational degrees of freedoms, the same amount of 3n coordinates, but they have a difference in rotational degrees of freedom because CO2 is linear. And by definition, therefore, CO2 has an extra vibration. So H2O only has 3, CO2 has 4. Okay, so let me just show you some cool examples of these, right? So what are these collective motions? Well, here are the 3 water motions. Let me put this on a new page. So here's some examples of water. So these are the water normal modes. Okay, there's 3 of them. There are 2 stretches, and there's a bend. Okay, because the center of mass has to stay constant, A symmetric stretch is not just the O and the H stretching. The O is actually moving, displacing upwards as well to maintain the center of mass. As two H's move out, so the H has to kind of pluck itself out to cancel out that change. So there's a symmetric one. There's an asymmetric one where this bond compresses and this one stretches at equal amounts. And then there's what's called the libration, which is the bend. Sorry, which is an extremely important motion with hydrogen bonding. Hydrogen bonding tends to coordinate most dramatically or break through these bending motions. Each one of them has a frequency, right? Each has a unique force constant. And of course, then some harmonic constant and some anharmonic constant as well. Have their own kind of their own parameters, and I can type in those frequencies. I can show you those frequencies. I just got to pull them up. Remember that the frequency is hc times the force constant divided by the reduced mass. Okay, so we can already, if we look at these as just OH bonds vibrating, we can kind of just assume roughly that the force constant is the same in all of them. Is that fair? Yeah, that's probably fair. And so the frequencies depend largely on the reduced mass of the displacement. Okay, so the larger the more mass moving, the lower the frequency. Okay, so in the symmetric stretch, right, it's just basically hydrogens moving. So mu is very small. Okay, so the frequencies of the stretches are going to be fairly large. In the libration, you actually have roughly equal motion of the oxygen and the hydrogens together. So that has a much larger reduced mass for that. And so the bend is much lower in energy, much lower by frequency than the others, because it just is kind of effectively a heavier vibration. So let's go, let me type in, let me grab the frequencies of these. So the frequency of the 0 to 1 transition, where you see the absorption. So this is at 3585 wave numbers. This one, the asymmetric stretch, is at 3506 wave numbers, right? And that should make sense that they're fairly close to each other, because the same bonds are being displaced. The only difference between them is a slight difference in how the reduced mass of the displacement is occurring. One has these two atoms moving out together. This one has it going in this way, this out this way. The masses are slightly different, effective masses of these vibrations, but they fall into the same category, right next to each other. And this one, much lower in frequency as we predict, 1885. It's great. All right. Again, you guys have seen these stretches and these bends and things. It's not a particularly new information, but it might be interesting how we arrive at this model instead. The last thing I want to look at, this tells you something about the frequencies of the vibrations, but what about the intensities? This was the conversation that we had last time. What makes a vibrational absorption strong? Remember, our conclusion was that the dipole moment of the molecule had to change. If the system, the dipole moment had to change, then the system absorbed that radiation. Gives it a bright transition. Exactly the same thing applies here. The dipole moment of the molecule has to change in order to see a vibration. Nothing new. Same calculation as before. Same symmetry requirements. So let's just do a couple of examples. Just want to show you the general idea of how we can think about vibrational intensities and what we expect to see in a spectrum. There's actually a really beautiful theory that you can learn in my spectroscopy class on how to really predict what transitions actually appear for any molecule. Right, well, in general, the derivative of the dipole with respect to each of the coordinates has to be non-zero for a transition to be bright. Just like we had before. All right, so let's look at some examples. I think it's nice to just kind of, you'll actually do this on the SO2 lab in this coming rotation, starting next week. And we can just kind of think a little bit about how structure is changing as we do a certain vibration and detect whether the dipole should change or not. So let's just look at here's some examples, for instance. All right, let's think about CO2. All right, CO2 has 4 vibrations. What we had earlier is 4 of them. I'll write all 4 down. So Q1 is the symmetric stretch. Okay, where this atom and this atom displace. Right, there is the asymmetric stretch, where one atom comes in and the other one goes out. And there are 2 bends. Which are equal to each other. They're degenerate, and we'll see why in just a second. One is where the atoms displace in like this. And there's one where the atoms displace in and out of the board. Okay. So they're the same energy. And so in order to see the vibrations of these, the dipole needs to change. Okay, so let's just kind of go one by one. Well, carbon dioxide does not have a dipole because the O's cancel each other out. So this system has no permanent dipole moment. But remember, we don't really care about that. We only care about whether the dipole changes. Okay, so if the system maintains the symmetry on the vibration, meaning both sides of the molecule are still the same after vibration, then no dipole has occurred. So the symmetric stretch, this O goes out the same distance as the other ones. So the dipole moment of this system is 0 still, because anything that this O creates is canceled out by this O pushing in the opposite direction. So the change in the dipole for this is 0. And so this is forbidden. We do not see this in the IR. Sorry, I ran out of space. All right. So you go look at CO2, it's not even there. Well, the asymmetric stretch, however, does induce a dipole, right? Because what I've done is I've broken that symmetry. This bond, in some sense, is now smaller than this one. So I'm pushing electrons in this direction. So I've induced a net dipole in this direction. So the dipole changes. Right? And so this is bright. It's quite bright, in fact. We'll go look at it in a second. And then what about the bend? Well, it's exactly the same thing. Here I've broken the symmetry again, right? But not exactly in the same way, right? These 2 bonds are still the same, but now what I've done is induce the dipole moment in this direction instead, along this direction. Right? I've moved the negative charges down and the positive charge up. So this induces a dipole in this direction. The delta mu for this is not equal to 0. And so this is bright as well. All right, so let's go look at the spectrum of CO2. Right, we expect to see two vibrations in the IR. Right? We expect to see the asymmetric stretch. We expect to see the bend. So here's an old spectrum of the thing. Right? And in fact, here you go. So right here, this is the asymmetric stretch of CL right here, the highest in vibration. And here's the bend. They're much smaller. 600 millimeters. So, right? You may notice that there's some other junk out there. That's interesting. What could that be? It's kind of an interesting combination. Right, so at the very least, we can identify that there are two peaks. But there's some other things out in the distance. I think that possibly be. Well, there are other ways to combine normal modes. Remember in diatomics, if I have 3 levels, there were 3 different types of transitions I could create, right? I could do the fundamental, I could do the overtone, and I could do the hot band, right? There are 3 different types of transitions with 3 different frequencies that the diatomic can give me. Now, what about a polyatomic molecule? Well, I've got at least one mode, V sub I equals 0, V sub I equals 1, V sub I equals 2. But remember, I've got multiple independent vibrations. So this is the IF mode. There's some modes, other modes. There's the IF plus 1 mode that has its own energy levels. Right? And there are 3n minus 6 of them. Right? There's 3n minus 6 of them, and each one of them have excitations. Right? I could go fundamental here. Could go fundamental here. I can go overtone. I can go hot band. Right? So I've got 3n minus 6 of sets of energy levels that are all independent of each other, and they can all be excited together. Right? So not only do I have the selections, right? Not only do I have here one overtone, one fundamental, and one hot band, right? And the same for this one, but I can combine them together as well. Right? So there's a new types of vibrations called combination bands. Which are collective vibrations of multiple modes excited at once. Right? So for water, right? I have V1 is equal to 0 to 1. I have V2 equals 0 to 1. V3 equals 0 to 1. Right? I have those fundamentals. I have the overtones and so on. Zero to 2. But I also have the combinations. Right? I could take V1 equal to 1 plus V2 equals to 2. And I can excite that from V equals 0. Right? I could have V1 plus V2 plus V3. I could have 4V1 plus 2V2 plus 3V3. Right? I can combine them all together in any combination I want. right? They're like, you have like a piano, right? You have a bunch of fundamental notes and octaves, and you can build chords with them. Right? And so we have these combination bands, which are just chords, right? You can do the Ramones power chord of your formaldehyde. Right? So we can build chords out of vibrational notes as well. And that's what those extra peaks are. All right. So when you guys do the SO2 homework or the SO2 lab in the third rotation, you'll actually see these combination bands and can start to appear as well. All right. That's it for vibrations. We're going to start hydrogen on Wednesday. Very slowly, but we'll get there. Have a good one, guys.